Welcome to the course on two-dimensional signal processing, principles and practices. We had learned to the 2D signals, how to plot them and visualize them. Also the basic signal models like step and impulse responses. Also, how do we use that shifted ones and combining them as product or summation in the 2D signals, and exponential signals, how do we visualize? And as we have seen in the 1D sequences, the decaying sequence cannot be visualized in 2D, but the amplitudes can be seen in the signal which is plotted. Also, we had seen the convolution, that 1D convolution. So, using the background of 1D convolution and the methods in which it is done, we'll do the circular convolution as well. And the convolution which we had done in 1D, that's a linear convolution. So the relation between 1D and 2D convolution we learn, and from that 2D convolution we will use the methods of 1D convolution and the circular convolution 1D in this lecture. So first have this circular convolution. Circular convolution, straight away take an example and explain that how to perform this circular convolution, and then we would relate this circular convolution when we learn the 1D DFT, and how this circular convolution will be more easier if we know the DFT. Now we are doing this circular convolution in time domain. That's taking a sequence x1 of n 2 1 2 1. So this sequence is first as index starts from 2, and then x2n also 1 2 3 4. This the same example which we had done for linear convolution. And then y of m, the circular convolution formula, n is varying from 0 to n minus 1, x1 n, and x2 m minus n, capital N. This is a modulo operation. So we need to understand what is this modulo operation is. So if you take that, just performing this circular convolution, it's a very popular method. So you visualize that in a circle, that first sequence x1 of 0, which has the value 2, 1 is value 1, and x1 of 2 is 2, and x1 of 3 has value 1. So taking the second sequence, x2 of 0 1, and x2 of 1 is 2, and x2 of 2 is 3, and x2 of 3 is 4. So you can see that these are arranged in anti-clockwise direction or the fashion. Once in this fashion, when we have arranged the samples, just perform the convolution. That means you multiply the corresponding indices x1 of 0 and x2 of 0, 2 and 1. So this multiplication, and similarly the respective indices 1 here and this is 2 here. So multiply them, the second one, and similarly the third one x1 2 and x2 2, which is 2 and 3 here, and similar the fourth position also can be multiplied, and add the sum at for m equal to 0. That's what the equation says here. That is 2 plus 2 plus 6 plus 4, it would yield 14. That's y of 0, the first circularly convolved value is 14. And similarly, if we continue for the second position, that m equal to 1, so we keep this first sequence as such, and then make the second sequence one position anti-clockwise. So you can notice that x2 of 0 has come to this position from here, and x2 of 1 is one sample moved ahead, and 2 is moved here, and here 3 is moved here. So now multiply these positions, that is x1 0 and x2 3. So it is here x1 0 and x2 3. So this corresponding positions needs to be multiplied, and then here x1 1 and x2 0. This is the second one, and the third one is x1 2 and x2 1. So this is the one, and here x1 3 and x2 2. This one. So corresponding position values, we take the product and add them together, that is 16. So for m equal to 1, the convolution results in 16. So for the third sample, that is m equal to 2. So again move the sample one more location or anti-clockwise. So that what you can see, x2 of 0 has come up from here to this position, and similarly all of them moved one position here, and then multiply, but we have not done anything with x1n, that's kept as such. So now multiply the respective values over here, 0, but this is 2. So you get this product, and similarly x1 and x2 3, that's the second one, and the third x2 0 and x1 2. So this is 1, and similarly x1 3 and x2 1. So this is the fourth one. So we add them all together, and this is yielding 14 again. And for the next value, m equal to 3, because we have the indices 0, 1, 2, 3 for m, because the sequence is also 4 samples each. So again, one more position, you can see that x to 0 has come to this position, and we have each one has been moved one position ahead, and with the respective position you can multiply 0, 1, 1 and 2, and 2 and 3 here, and 3 and 0. So that's what we get from this. It can the summation is resulting 16. So the circularly convolved sequence m4, that would be again coming back to the if you move it once, it will come back to the original position. So we'll stop at this point. The convolved value is giving 14, 16, 14 and 16 here. So the length, if you notice, it is different from the linear convolution, and this is equal to the sample number. First one is having n1 suppose, and the second one has n2, and that is equal to this circularly convolved sequence length. So if one of the sequence is lesser in length, so make both the sequences by equal by appending zeros, and then get the circularly convolved sequence. Now, can we use this equation directly? So yeah, for m equal to 0, this m is 0, x1 n is varying from 0 to 3 the indices, and x2, this m is 0 minus n modulo 4 samples here length. So if we take that values, this is for n equal to 0, this is 0, and here this is also 0, whereas for n1 you expand this, and this one would be 0 minus 1. So this becomes minus 1, and then next it become minus 2. You can see the changes it is. So what is the sample value for it? We in our original sample we have 0 sample, first sample, second and third. So what would we do it for x2 equal to minus 1 or 4? Which sample it represents? So here there is no problem in the case of the first one. This is 0th sample itself, but when we go to the minus 1, so the minus 1 indices is corresponding to third one, some 0, 1, 2, 3. In this 1, 2, 3, that minus 1 represents the third one, the last one, that is 4 minus 1 here, that is going to be 3. Then here 4 minus 2, that's second sample itself. 4 minus 3 here is going to be first sample. So you can see the modulo operation, which has been replaced with the existing samples only, and then do the multiplication and summation, which would result in 14, the same thing. So if you continue this procedure for the second case also, where m equal to 1, and you have this modulo operation at 1 here, and this is 0, there is no issue. These are positive indices which is there already, and but in this case the negative indices doesn't have, this would be replaced with x2 of 3, and this will be x2 of 2. So if we replace it and get the sequence, 2 into 2, 1, 1, and this is going to be 16. And we similarly we get it for m equal to 2 as well, that is 2, this becomes 2 minus n modulo 4, and we have the equation, the x1 0, x2 4, and this x2 1 4, and similarly 0. So these 3 samples no problem, but here x2 of minus 1, this needs to be replaced with x2 of 3. So that replacement and substituting the values of it would result in 14 again. The same sample values you can give. So m equal to 3, the equation now become 3 minus n. So there is no negative indices coming up in this, because this is 3 and n is varying from 0 to 3. So we have the last sample is 0 inside. Then the existing samples can be substituted and added to get the 16. So the circularly convolved sequence, again you can see the same result where we get the 4 samples, 14, 16, 14 and 16. Now this can be done easier way also. So take the first sequence sample of all of them, 2, 1, 2, 1, and push it once. This is, you fill it here and take the first sample to the next one. And similarly you can do it in this fashion also. You can arrange it here, arrange it in this fashion. The 4 rows you would, with the first 4 samples, and again pushing it down, you'd get this way. So you get the 4 columns, and the second sequence is written 1, 2, 3, 4. Now multiply this as a simple matrix multiplication, and then you get the values of it similarly 2 into 1, 1 into 2, 2 into 3 and 1 into 4, and then you add up together. So the first one would result in, this is 14, 16, 14, 16, you would get it. You can keep this sequence in the first, and that is shifting it, and then put this 1. Also a method of doing the circular convolution, the second sequence is taken in this way, multiply them and you get this same sequence. So the order doesn't matter in this case. So this is how the circular convolution is done. So what is the relation between this linear and the circular convolution? So for linear convolution, the resultant, if you recall, the resultant sequence is having this length n1 plus n2 minus 1. But for the circular convolution, this was n1, first sequence has n1 and second sequence has n2, and make this sequence as n equal, and the length of the sequence would be n. So the circular, what is the relation between these two? So the x1 n, so this is going to be the circular convolution notation. So we'll be using in 2D as well, and this is 1D what we are doing now, and this is a linear convolution, x1 and x2. The asterisk and asterisk is provided with a circle when these two convolution would be equal. So if that is n, the length of the sequence is greater than or equal to n1 plus n2 minus 1. So the length of the sequence is n1 in first case, and second is n2, and the resultant is resultant linear convolution would be 7. So if you make the each sequence length 7 and more, then the linear and circular convolution result would be same. So the linear convolution resulted this value of 7. So where the same value you would get by doing the circular convolution also, and making the sequence length each 7 and perform the circular convolution. So after making this n and perform the circular convolution, that will be equal to the linear convolution. So you can the circular convolution output was this, but when you make the length of the each sequence 7 and perform the circular convolution, that would result in this linear convolution resultant. So the condition for the linear convolution is n should be at least greater than or equal to n1 plus n2 minus 1. So that is the relation. We would see the same thing in the two-dimensional signals as well. So now with the convolution background, we would learn 2D convolution. What is the 2D convolution meaning here? So the signal x of n in 1D now written in x of n1 comma n2 and h of n1 comma n2. So this asterisk, generally when we say in 2D convolution, we will put it 2 times the asterisk. When you use one asterisk with 2D signals, that means the 2D convolution also. Y of n1 comma n2 is x of n1 comma n2 and h of n1 comma n2. So the summation x of k h of n minus k now change to x of k1 comma k2 and h of n1 minus k1 and n2 minus k2. So this shifting in each indices and summation resulting for k1 one index minus infinity to plus infinity, and similarly the second index k2 minus infinity to plus infinity. So now the change, the same 1D convolution equation is now expressed in the 2D convolution as or instead of having x to change it to k base, we can change the h to k base. That means in 1D we also do that, it is h of k into x of n minus k. So the summation. So this both are equal. So the indices k1 and k2 varying from minus infinity to plus infinity in the summation. Instead of x, we can have h k1 comma k2, and instead of h here we can have x n1 minus k. So both will result in same. So the ways both in which this 2D convolution can be performed. So the size of this, the first sequence is n1 into n2, that is, no, it is not the convolution. Here we mean that it is a n1 size of the sequence, this 2D signal, first signal, and this is m1 into m2 or the 2D sequence sizes. One is n1 n2 and or n1 cross n2, m1 cross m2. So which would result in, if you perform the linear convolution here, there is n1 plus m1 minus 1 the first, and the n2 plus m2 minus 1. The length of the sequence would be this. So now we would see how do we perform this 2D convolution. So let's take a sequence x of n1 comma n2 in which you can see this value is 2 and 5, 3 and 1, 4 and 1. So you can have any sequence. So n1 is varying from 0 to 2, and n2 is varying from 0 to 1 only. So this sequence has in the matrix form, that is going to be 3 into 2, okay, and this is 2 by 2. Okay. So taking the second sequence h of n1 comma n2 is 1 minus 1, 1 and 1. So these values are given, and you can notice the indices. This is 0 0 and this is 1 0, 2 0, 0 1. The 0 0, 1 0, 0 1 here. So that means n1 is 0, n2 is 1. So that is the representation. So if we taking these two sequences, how do we convolve the two? Now we take the first sequence, change it to x of k1 comma k2. The base of n1 just changed to k1 and n2 to k2. The values remain same, 2, 5, 3, 1, 4, 1, all of them. And h of k1 comma k2, this also changed to k1, k base, k1 and k2, not in n. Okay. And the indices are represented here. So now take one sequence, either x or h, take a mirror image of it. So we use the h for shifting, h of the first equation in that 2D convolution, x of k in h of n minus k summation for the 2 dimensions. So we use h of minus k1 and minus k2. So the mirror image 1, 2, 3, 4 samples are the first quadrant samples. When you take a mirror image, it becomes a third quadrant samples. So you have one here, and this one would be, this one goes to this point and minus 1 comes here. This is going to this position and this is going to this position. So that is one here. So you get to the 4 points over this h of minus k1 and minus k2. So in the equation, what we have here is h of minus k1 and minus k2, and then the sequence x of 1. So let's see how do we compute the value y of n1 comma n2. So the first one is h of minus k1 and minus k2, that's a mirror imaged h of k, and the sequence is kept as such. Now taking the equation here, k1 comma k2, h of minus k1 minus k2. So if this is the equation for n1 and n2 0 0. So we are going to get this sequence in this. So if you see the product of these two, h of minus k1 minus k2, the having this sample, and x of k1 and k2, this sample are the common sample in these two sequences, whereas these positions and this positions, there is no samples here, it's 0, and similarly for this 2 there is no sample here. So that means if you take a product, only this one and this one result in one value, which is 0 comma 0 for 0 comma 0 equation. So you get 2 here, this is 2 and 1. So multiplying you get the amplitude of 2. This is the first 0 0 index we get. So similarly, if we take the next one, that is here 1 minus k1. So what do we want to, h of minus k1 and minus k2, in adding this mirror image plus 1 here. That means the one which was here is now pushed to one sample advanced in this fashion. So now this one was in origin, now it has come here. It was in this left hand side, it has come here compared to the h of minus k and minus k2. Now the 1 minus k1 and minus k2, and x is kept as such, that's the value. Now we find the product or the common between them, common sample between this. The first common sample here, so you can see this 1 2, this is here, and you have these two values 2 5 and then minus 1 and 1. So when we make the product, so these points result in 0, and this point also that we don't have anything here, and these two would minus 1 and 2 it result in minus 2, 1 and 5 result in 5. So we add them together to get this 3. So the equation y of 1 comma 0, that is here we have made this 1 comma 0 in this equation, that is 1 minus k1 minus k2. So minus 2 results from this minus 1 and 2, and here 1 and 5, which is multiplied, we get minus 2 plus 5, which is equal to 3. So the second point in y of n1 comma n2, that is y of 1 comma 0, is obtained in this fashion. So what we did is h of minus k1 and minus k2 and shift this in one direction, that is k1 direction. Okay. So now if we want to suppose have h of 2 minus k1 for the y of 2 comma 0, in that case what will happen, this k1 and k2 are resultant, only this one becomes 2 here. So 2 minus k1 and minus k2. So h of minus k1 and minus k2, what we got, that signal needs to be shifted once more. So we get h of 2 minus k1 and minus k2 results in, you can see this point is shifted to 2, which was at 0 in the mirror image. So now the two samples are shown here, and x of k is as such, that is 2-dimensional signal. Now what is the common sample points available here? So this and this here as well. So we have here, you can see this 2 would result in the point which is minus 2, common minus 1 and 5 and 1 and 3. So product and sum it, so we get minus 2 here. So the equation which is minus 5 minus 1, the product, and the 3 and 1 product would result minus 5 plus 3, which is equal to minus 2. So that's the third sample. This is how every sample of y of n1 comma n2 is obtained. Now what we got is 2 comma 0. So similarly we can shift it further and we'll find the common area. So if it doesn't find common samples in between the two, so then the y of n1 comma n2 would result in 0 comma 0 actually. So these samples would end this operation. How many shifts we have to do? So what is the region of support in this case, that we would see for generalizing the region of support. But similarly, if we can move this way, making this y of 0 comma 1, okay, and 0 comma 2, can we find that? So in the next case, so the h of minus k1 1 minus k2. So if you want to shift it up, this needs h of minus k1 and minus k2, which was here in this third quadrant. Now you can see this shift which has gone up one position in k2. So h of minus k1 there is no shift, in k2 it is going one position up. So this is the resultant sequence h of minus k1 comma 1 minus k2. So now the sequence xk is as such. Now we will find the common samples between them. So this common samples, here it's 0 0, it is there, and here there is none, and here there is none, and there is here and here as well. So now the common two samples are these two. So now multiply the same positions, 1 and 2 result in 2, 1 and 1 result in 1, adding them together result in 3, that is y of 0 comma 1. So here this is 1, and then so y of 0 comma 1, which results in 2 plus 1 is equal to 3 here. So that's how we have obtained the 0 comma 1. So similarly it can be extended till that there is a common thing. So if we further move it, that is 2 minus k2, so this would be matching with this. There is one more point we can get. After this, there won't be no common sample between this, because if it moves up in this direction, so this would result in 0 here. So if we continue this minus k1, 2 minus k2, so this has gone up one more sample, 0 0 is here. So x1, so you have this two samples here, so 0 comma 2 would result in here 1. Okay, so that is 1. So which is one sample, and this sample, because there is no other sample here, would result in 1 here. So similarly, if we continue this operation, actually whatever this, we would continue the operation, so we would get the product, or the case of convolved sequence. Here's 2 3 minus 2 minus 3 and 3 10 5 2 1 5 5 1 in this fashion. So how do we know that this 2D convolution where to stop? What are the region of support for each 2D signals? Supposing we know the first sequence has the region of support, here this is P1, Q1 and R1. There is something depending on P1, R1 and Q1, here also it would be some value. If that is the case, if we convolve this with another signal sequence which has a region of support P2, Q2 and R2, and depends on R2 and Q2, this can be a different value. So, in our example that we had taken, it was starting from 0 0 and here also 0 0. The first sequence was 0 0 and the second was 0 0, and the resultant convolved sequence will have P1 plus P2, that is 0 0, this 0 and this 0, first index would be added, and this would also be 0 0. And similarly R1, what is the index we had? This was 0 0 and you would get 0 0 here. The second one, it is 0 1. In our example, this R1 was 0 1 and then R2 was also 0 1. If you recall, that is X and H two sequences, and this would add 0 0 R1 plus R2. So, the sequence would be 0 2 here. So, 0 1 and 0 1 adding together, it would get 0 2. So, the maximum we can go in this direction up to 0 2 in the convolution process. After that, it would become 0 then. So, the region of support what we get here is 0 2, and similarly for Q1 what we had in one sequence, it was 2 0, that is X sequence has 2 0, and in the another sequence it was 1 here, 1 0, and we add those two and the resultant would be this is 3 0. So, the resultant would be only addition of the two. So, we can easily find in 1D we can say the linear convolution n1 plus n2 minus 1, the length of the sequence. So, whereas in 2D we need to find out the indices and what should be the region of support of the 2D sequence. So, this is 2 1 based on the sequence what we had in the first case, and this was about 1 1. So, if we add them together, this would be 3 and 2. So, we had 3 in the n1 values and 2 in the n2 value. So, that is the output which we had got in the previous example. So, this is the generalized region of support to way in which we get the region of support for the 2D sequences. So, 2D convolution length, what should be the length of the sequence or region of support for the convolved sequence. So, if we try to find out, so first we need to know the length of the sequence, 2D signal, one signal and the other signal and the indices of it. So, adding all this indices would result in the indices of region of support of the convolved sequence. So, we had seen the 1D convolution and the 2D convolution based on the 1D convolution. We had also introduced the circular convolution. So, we would dig out more on this circular convolution when we do the DFT and what is the relation between this DFT and the circular convolution. Using the circular convolution and the linear convolution, how when these two convolutions are equal, and practically what is the meaning of these things will be discussed in the next few lectures. Thank you.